All right, on 21, that was actually, and I see why that would be a little difficult, but not quite sure how to show that, right? I mean, basically they want you to show this. Why is the trapezoid rule that? Isn't that what that one was? Left plus the right divided by 2. Okay? I think the easiest way is to do it, come back to this. Now, there would be some other ways. I mean, you could draw a picture here and show that a trapezoid is this and do an average and do a little geometry work and that kind of stuff. And that could work too. But I think the easiest way is to just say, well, let's just add up L and R. So just add this with this. Well, if you added these two, I think I actually kind of went through this one day. If you add these two together, well, before you can add them, you'd have to factor out this part, right? So if you took this and this and factored it out from those, you'd have b minus a over n out in front. Okay, so that's the b minus a over n you see here, right? And if you factor that out, then you would just add together the stuff inside. Well, what would you have? You'd have one of these. You'd have 2 of those. 2 of those, right? You'd have 2 of everything else. And then you'd have 1 of the last, right? And then when you divide by 2, that's where that 2 would come from. That make sense? So if we just take this plus this, we can see that it ends up being this. And that's really all we want you to do. Okay? All right. Well, if there aren't any others, let's just read through our answers to 35 through 46, and then we'll move on to the new stuff here today. So 35, what do you have? May. 36? Must. 37? May. 38? May. 39? 40? Cannot. Right? Because that has midpoint trapezoid, and that one was concave up. Concave up. Trapezoids have to be over concave up. So there's no way trapezoids can be less than midpoints, because they're over, midpoints are under, so cannot. 41? Must. 42? Must. 43? Cannot. 44? Cannot. 45? Must. And 46? Must. Must be true. Okay? All right. Well, if that is it, let's get your notes out and move on to the next section. So now this section 6.2 is all right, so in your notes, write down this problem right here. This is our favorite old function that does not have an antiderivative. Okay, does not have an antiderivative. So get your calculator out. Here's where Sam is going to lead the way. Okay, so get your calculators if you've got them, and we will use that area document here just a little bit. So Sam, you'll have to get that opened up here at some point. Uh-oh, we have a problem. That's okay, Sam. Don't worry. We'll still let you be presenter. Yeah, that's. So you are going to have to log in again. I'm sorry. Yeah, we had to send ours back.
So you send it in to bring back a new one, but it's still out.
Good thing I'm a PS3 user. What did you
Okay, log in again, please. Log in again. Sam for sure.
It did not go soaring over my head. Oh, look at. Oh my gosh, everyone around me.
Dang it.
Yeah, but she won't be here tomorrow.
Huh?
I really just don't think it wants
I got
It,
footrest.
well, now this happened to somebody in second block too, and
Does anyone
it-
like orange?
it eventually worked.
things?
What? Those jelly beans?
Do you like the orange ones?
Yeah, absolutely.
I hate the orange
If I would
ones.
have brought you a crispy chicken sandwich from Wendy's today, would I have still have to
I would say I probably would have let you out of it.
You guys were right.
I think I would have let you out of it.
You threw it away.
You threw it away?
Yeah, you threw it away.
Oh, my.
I told him to bring it to you.
They,
Why would you throw a sandwich away?
they,
Couldn't eat it.
But there's hungry
they gave you
I
a,
mean, one disc.
people. He's a hungry.
they gave you an extra or something?
It took
Oh my gosh,
this
this
is
is all
they told him to bring it to you. And he was like, oh no, he won't want
Yeah. You are now you are the full-time presenter the rest of the year. You're-
watching that crazy. Wait. Watching that crazy.
all right, log in again.
Yeah, it's like, I hope this isn't me.
Again?
Log in again, yes.
Do we have hands?
You're right, just Sam needs to log in, actually.
Ham is heroin.
There we go.
Okay, come on now.
Put it on random. See who gets
Aha, we're in. Okay, so now, go to a calculator screen and just do this integral right here, 0 to, now everybody else can participate along on your own calculator, wouldn't hurt you to rub through this at all. So sine 0 to 2, now sine of x squared, now remember, we do not know the antiderivative of this one, right? So we do not know the exact answer to this definite integral. Because we can't use fundamental theorem part 2. So when he hits enter here, he gets this. Now go ahead and just do plain old x squared. Do it again, do 0 to 2 with plain old x squared, okay? Just do the integral from 0 to 2 of plain old x squared. And in this case, when you type it in, what is the answer that it gives you? 8/3. What's the calculator doing on that one? Antiderivative. It's doing fundamental theorem. It's giving you an exact answer, not a decimal. But on the first one, it couldn't do an antiderivative. So what's it doing? Some sort of approximation technique. Now, is it doing left, right, midpoint, transpoint, Simpson, or some other more complex one? Probably that, the last one, probably some more complex one, even than Simpson. And we'll talk more about that. But so the idea here is that our whole goal here today is how, and what was that answer again, Sam? Read it to me. Yeah. Give me 3 more. Okay, and it keeps going. So the whole question now is, how does a calculator know that that's it? And how accurate is it? Now, right, because sure, the calculator could say, well, let's just do 1,000 rectangles, or let's do 100 Simpsons, or whatever, and then just throw that answer out there. But how accurate is that, right? Is it, are the first 2 decimal places right? Are the first 3 decimal places right? The first 10? How many is it? Well, I believe the calculator is set so that all of the ones it shows you are correct, right? And so let's say it shows you 13. So somehow the calculator is guaranteeing that it knows the right answer to 13 decimal places. Now, how can it possibly know that? If it doesn't know, if we don't know the exact answer, how can we know we're right to 13 decimal places? That's what we're trying to investigate today. How can we possibly know that? All right, if we don't know the exact answer, how can we know when we're this close? Okay, so that's what we're going to be going through. All right, so the idea is going to be this. What causes, I mentioned this yesterday, what kind of a graph would a left and a right rectangle be perfect fit for? No error. Horizontal line. Right? Horizontal line, a left and right rectangle would be perfect. So what is it that makes a graph not be perfect for a left or right rectangle? Not being a horizontal line, having slope. Now that's if it's a line. If it has a curve, of course if it's a curve it also has slope, right? And so what makes the error worse? What makes left rectangles be worse for one function versus another one? The steeper the graph is, right? Think about it. The steeper the graph is, the worse a left rectangle will be. So if I've got a graph that's just kind of does this, left rectangle's not bad. But if I got a graph that kind of is going way up like this, then a left rectangle is going to have more error. So if we're going to figure out how far off is an approximation, and how does a calculator know how far off it is if you don't know the exact area? How does it know how far off it is? We got to know what causes it to be off. What causes the error? Okay? Well, so what we just figured out here is that steepness causes the error. Now we're focused on left and right right now. So here's what we're going to do. We're going to take our function, whatever it is, and we're going to figure out where its slope is the steepest. We can do that, right? Get the slope from the derivative, right? So we can do the derivative, f prime, and we can figure out where that's max, right? Now we're going to cheat. We're going to let the calculator do most of the hard work on that for us, right? We're not going to do the max, min, number, lines, all that stuff, okay? But if we could find where f prime was the most, that's where the graph would be the steepest. And what we're going to do is we're going to assume then that the graph has that steepness the whole time. Now think about that. Wouldn't that be the most error we could have? Is if we found where the graph was the steepest and we pretended the graph was that steep the whole time, like a line. Wouldn't that be the most we'd be off? Okay, so we're going to call K1. That's going to be K1. K1 is going to be that number. K1 is going to be the max slope of f. Okay? So that would be like calling it f prime. Okay? So, actually I shouldn't call it f prime. I probably should call it something else. Because f is our graph. So we'll call that g prime. Okay, we'll call that g prime. So then the function g would be like a worst case scenario graph. Right? So what I just did was an antiderivative there. Okay, I just did the antiderivative of k1, right? The antiderivative of g prime would be k1 times x, right? So if we had a curve and we found where it was its max slope, and we said, what if we had a curve that was that same slope all the time? Of course, that wouldn't be a curve, it'd be a line. But, right? And that wouldn't that be the equation of a line like that? K1 times x, right? Again, K1 is worst case scenario. The steepest the slope ever is. Okay. So what I'm going to do, so let's take this picture right here. So let's pretend that this, we'll turn it into a line. Let's pretend that this line right here is the line K1x. Okay? So this, and this is just for one rectangle. So this red right here would be how much we're off, right? Now that would be the max amount of error right there. Okay, so what I want to do is find that red amount right there. So I'm going to call this my starting point. I'll call that 0, and let's use h to represent one width. That's just like we used to use h for delta x when we did our slope calculations way back in the beginning. So 0 to h. Okay, so that's just, okay, we're going to just talk one, and it's going to be a left rectangle. It'll be the same for right, so we'll just go with that. Okay, so I want to find that red amount. Well, what would that red amount be? Well, it would be the area under this function. Are you with me? It'd be this, if I took all this area right here, right, that would be the integral from 0 to h, k1x dx, right? That would be the blue area, right? That would be the area under that line. And then subtract what? Subtract the left rectangle, right? So subtract that one left. So let's subtract the area of that one left rectangle. And those two together ought to give me the red area, right? And again, what's that red area? The max amount of error, right? Now, why is that the max amount of error? because that K1 we're pretending is the steepest slope the function ever has, and we're pretending it has that the whole time. Okay? So keep those things in mind. All right, so this integral, this blue integral, we can do pretty easily. K1 is just a constant, so we raise that up to a 2, divide by 2, so that'd be 1/2 K1x squared from 0 to h. Plug in an h. We have 1/2 K1 h squared minus, and then that'd just be 0, right? And then we subtract the green. Now what's the green? The green is this left rectangle. Now what would be the area of this left rectangle? Well, that would be a height of h, and then what would its height be? The width of h, I'm sorry, width of h, and what would its height be? It'd be the g at 0, right? It'd be g at 0. Well, what's g at 0? Here's g right here. You put a 0 there to 0. Well, that makes sense, because K1, a line like K1x, that'd just be a line right to the origin. So it's 0 to 0. But it wouldn't matter. The algebra is easier if we go from 0 to h. We could have went from h to 2h, or 2h to 3h, whatever, right? It works out. So that's going to be 0. Okay, so that's going to be 0. So it turns out that the red amount of area, the red error, is 1/2 K1 h squared. Okay, now I'm going to do a little rewriting of this. Now that's just for one interval, right? That's just for one rectangle. How many rectangles do we have? N, right? 100,000, N. We'll call that N. So what I need to do is I need to multiply that by N to give me the total max error. Now what I'm doing now is I'm taking that K1, the steepest the slope ever is, and I'm pretending that it has that slope the whole time. And then finding out how much error there is. And that's my worst case scenario. That's the max error. Okay, now I'm going to do another little thing here. What's another name for h? This is one width. We call that delta x, right? That's just the width, 0 to h. So h is just the width. And what was our little formula for width? What's our little formula for width in these problems? B minus a over n. So I'm going to substitute that in for h. So I'm going to come down here. So I'm going to have n times 1/2 times K1, and in place of h, I'm going to put b minus a over n. So I'm going to substitute that in for h, because that's all h is the width of one sub n. Okay, now let's do a little work on this. The 2, I'm going to leave that on the bottom. Okay, I'd have a K1 on top. I'd have an n on top. I'd have a b minus a quantity squared on top. And then what would I have on the bottom here? 2n squared, right? Because it's square the b minus a and square the n. And then anything else I can do? Cancel an n, can I? And cancel an n. All right? And there we go. We have that right there. Now, what is that red thing again? Max amount of error that a left rectangle approximation would have. The max amount of error that a left rectangle approximation would have. So let's write that on a new page. And this is in your book, actually, what they call Theorem 3. So in your homework, when they talk about a Theorem 3 error bound, they're talking about a max error problem. Remember when I did the thing with money yesterday? I said, what's it? $100 million is the upper bound of the money I have in my pocket. Right? That's the best case scenario, I guess, in that case. But that would be the absolute most I could have. I couldn't have anything less than that. But okay, so that's what we're saying when we talk about error bound. We talk about the max error. Okay, so here's how we would write that. We'd say I minus L sub n, and it would be the same for R sub n. So we could substitute that. Remember, isn't this how we wrote error? All right, so remember what this means? This is the amount of error, right? Everybody with me on that? This is amount of error. The actual area, which we don't know, minus the approximation, that's the amount of error. So we're going to say that's less than or equal to. So that means this side is the max error, right? If we say our amount of error is less than or equal to some number, then that number is our max error, okay? So that's our formula. K1 parentheses b minus a squared all over 2n. So that's on page 387, I believe. and it's in theorem 3. Now we're going to do one for trapezoids, one for midpoint here in a minute. We won't go all the way through it like we did that one. Okay, but that's our formula. Okay. Now there are two types of problems we can do to use this formula. The key, of course, is going to be what K1 is. Let's write that down as a matter of fact. What was K1 again? So it's the max of f prime is what that is. That's the max of f prime, the steepest slope. Now we got to talk about steepness here a minute. If you had a graph that had its steepest that it went up was a slope of 3, but the steepest that went down was -8, which part of that graph would cause the most error? The -8, right? So we don't really care if it's positive or negative, do we? We just care about what's the steepest. So when we say the max slope, what we really mean is the max of the absolute value of f prime, right? -8 is not really a max when you compare it to 3. It's more of a minimum, right? So we'll put bars around it, and that will tell us, okay, it's the steepest it is, okay? So that's an important concept of what K1 is, and we're going to have to find that. We'll use our calculators to do it for us, okay? So let's do a problem. There's a couple different types of problems that we could run into. So one type of problem is, now you can see where we're headed. If the calculator is going to know that it's accurate to 10 decimal places, it has to know something about how much error there is. And how can we know how much error there is if we don't know what the exact answer is? Well, what we're doing, we can say, well, what's the worst case scenario? What's the most it could be up? And then we go from there. So that's what we're doing. So here's a problem that we could have, and it would be, what is the max error? They won't say it quite like this. They might say error bound for L10. Now, when I say for L10, I'm talking about the original problem you guys did a minute ago. 0 to 2 sine of x squared dx. Now, we know the exact answer is what? 807, no, 80, what was it, Sam? 4776. Now, pretend we don't know that, okay? Pretend we don't know that, all right? But that's the exact answer. But what we want to know is what's the max error that 10 left rectangles would have, okay? So we're going to use our little formula. Well, first of all, we need to know what L10 is. Well, we don't need to answer the question, actually. I tell you what, let's don't do L10 yet. Well, let's just answer the question. What's the max error? Well, according to our formula, I minus L10, okay? And now we're going to do that little formula that we just learned. So let's put in the stuff. Well, K1 is going to come in a minute, so I'm going to put a box there for K1. Okay, I'll put a box right there, see what K1. All right, and then what's the next part? B minus A, so what do I put there? 2 minus 0 squared over. So 20, 2n, because n is 10 in this case. So 20, all right? So let's go ahead and let's calculate that out. Oh, wait, we need to know what goes in the box. We need to know K1. K1 is the max of f prime. Okay, well, what's f prime? You can let the calculator do it, but it'll be 2x cosine x squared. But we can let the calculator say, so let's get on our calculators. And Sam right there, yeah, go ahead and do the derivative of sine of x squared. Okay, and there it is. All right, now here's going to be the fastest way to find the max of that. The fastest way is going to be to graph. So go ahead and go to your graph screen. And let's graph that 2x times cosine x squared. Sure, put a times sign. Oops, that's going to be a problem. Yeah, got to put a times sign. There we go. 2x times cosine of x squared. Okay, what do you suppose we want to do next? Window. What's our window? 0 to 2. Okay, let's set our window 0 to 2. Okay, that's all we got set. And then what we say yesterday is a good thing to use? Zoom fit, right? So let's go 0 to 2 on our x's. So go 0 to 2. Okay, now let's do a zoom fit. Although that's not a bad fit right there, but not everybody's is probably the same. So we do a zoom fit. Now, where do you suppose that max number is going to come? Okay, but I mean on that picture. Okay, so where's it going to be? No, this is F prime. So it'd be right here. Isn't that where we want? Right, that's the example I just gave. If you had one that was 3 and one was -8, you want -8, right? That's what we're seeing. We're going to ignore the negative. We're doing absolute value. Now, we could have had Sam graph the absolute value of 2x cosine x squared, and then everything would have stayed positive, right? Or just pretend that this flips up, right? But basically, we want this max, but whatever it's positive. So trace down to there. Now, you can get there quick. It's close to 2, maybe 1.8 or something. It's pretty close to 1.8. You just type in 1.8 and get there pretty quick. And the nice thing about this is it'll trace right to your minimum. Right there. There you get it. Okay, now move your cursor around a little bit so that word minimum gets out of there. There you go. Okay, here it is. Here's the number we'd be looking at right here, right? Now, we got to think about this a minute. What do we want K1 to be? What was K1 again? The most slope that we can, not error, but slope, right? K1 is the most slope it will ever be. It'll never be more than that slope. Would it be appropriate to write in the box 3.58781? Now, it's a little bit of a technicality, but would that be appropriate to write 3.58781? Is that the biggest value on this picture? It's not, because you know what comes after this one? Probably, well, we don't know, but probably something else, right? So 3.58781.2 maybe. So would 3.58781 be the biggest this ever gets? No. You see what I mean? So we better round up somewhere, right? We better round up when we're doing K1, because remember, we want it to be a worst case scenario. But now, so let me ask this. Would 4 be a worst case scenario for the slope of this one? Would 4 be appropriate to be the steepest slope this one ever is? It's less than or equal to. Is the slope ever more than 4? No. Would 8 be okay? Would 1,000,000? Right? But see now, but what's wrong with that? It's not as helpful, right? Like what we were talking about yesterday. Right? With $1 million in my pocket, it's not very helpful, right? So we want the most, we want it, there's a trade-off. You know, how exact do we need to be, and what's a trade-off for what we need to do? For this one, and it varies depending on the number. To me, this one is 3.59 would be good. I don't think we got to go way out to here. But I don't think 4 would be that great. 3.6 probably okay. But I don't think, because 3.5 to 4, that to me, that's a fairly big jump. Now, what if this number was 103.58781? Would going to 104 be okay? Yeah, I would say so. 103.5 to 104 is not a very big jump. But from 3.5 to 4, I think it's a pretty big jump. So to me, I would say like 3.59. Is the slope ever going to be bigger in this piece of graph than 3.59? No. Okay. So that's how you find the K1. You graph F prime in that window, and you find what its max is. Okay, so back to our notes. So right here, we're going to put 3.59. Because now what we're doing when we plug it into this formula, keep in mind what's happening, is we're pretending that this function has that slope the whole time. We can clearly tell from the graph it does not. It does not have a slope of 3.59 the whole time. But we're doing worst case scenario. We want a guarantee. We want an ironclad guarantee of the accuracy of our answer. All right. So work that all out. What do you get? 0.718. So what's that 0.718 mean again? Max error. That's the most that L10 is off. Now what we haven't done is actually compute what L10 is. So let's do that. So let's remind, for those of you that were gone, what you're going to do is grab that area thing that I sent to you. Get that area document, which is actually stored in the mylib folder. I sent it to you. It's in the mylib folder. Okay, let me know if you can't find it. Just called area. You find it? Zach, you find it? Where you find it? Okay, open it up. Now yours might look a little different than this, but what you want to do is go to the window 1.2. Actually, you want to do something first. Go to dock. Go to the dock button. Sam, show them this. Go to the back button and choose Refresh Libraries, number 6. Did we do that yesterday? Oh, okay, maybe we don't need to. All right. So now, back into your document, I want you to go to page 1.2. Okay? Now, let's do this one. I want more decimal places, so we're going to choose. So, Sam, we're going to do the left, and I'll talk with you guys when we get a chance here. But we're going to do a left Riemann sum. But that's what this will do, is it will do these for you. So if you have double-digit or more subdivisions, you can use this document, 10 or more. So we're going to do 10 lefts. So Sam is going to type in RSL, which stands for Riemann sum left. Oh, yeah. Right up here. Oh, yeah, you guys are probably going to have to do this. You're going to have to define, it can't be f of x, so it's got to be f1 of x. Delete that just so they can see it, Sam. Let's just do it. So you can type the word define, or you can go up to menu and actions and find define. So we're going to define f1 of x, f1 parenthesis x to equal sine of x squared. So yes, we have to define our function first. Okay, so we do that, hit enter. Now we're going to type RSL, which stands for Riemann sum left, and then parenthesis, and then we have to go B, comma, A, comma, N. So since our integral is 0 to 2, we go 2, comma, 0, and then we do 10 for 10 lefts, and hit enter. All right, so 0.87160. So we get 0.8, what was it? 7, let's go 6 there. 5, okay. All right, and we know it would go more now. So that's 10 lefts. Now we can cheat a little bit, and we can see that that's not bad, right? I mean, that's not bad for 10 left rectangle. Okay, we're cheating by looking up here a little bit. So let's look at this. So what we're saying here in doing this calculation is we're saying that the most we're off is that much. Now, that's quite a bit. If our answer is 0.8 and we're saying we could be off as much as 0.7, right? I mean, it's not that useful of an error bound, but at least it's a guarantee. So here's another thing I can ask you. Give me a range where you know the exact answer is in between. Give me a lower and upper bound. Well, what would be a lower and upper bound of the exact answer if you know this is the max error of this? Couldn't you just add this on, right? You could add this onto there and subtract it. Why don't you do that for me real quick and tell me what those numbers are. What do you get if you add it on? And the upper, okay. So what we know is that the exact answer is somewhere between 0.1 and 1.5. Now, that's not that great, right? It's not that useful. However, let's do the same thing with L100. Or no, let's even do L1000. Okay, let's do 1,000 left. So now we go back to our little calculator program, and now we can just do the RSL, or we can change it to 1,000. And thanks a little bit. Well, yeah, it takes a little while to calculate 1,000 left rectangle, right? So you'd expect it to have to think a little bit. Okay, 805532. What was it? 5532. Okay. Now, let's do our little max error calculation for this one. So what would we put in the box? That wouldn't change, would it? We're going to do 1,000 left rectangles. The function's still the function. K1 is still the max of f prime. So 3.59 would still go in the box. What would go in this part of the formula? Same thing. What would go on the bottom? Instead of 20, it would be 2,000. So let's go ahead and calculate that. Actually, that'll be pretty easy because it's, you can do it right on this page. That's fine. So 3.59 times, what was it? 2 squared, that'd be 4, right? Or, yeah, 2 squared, there you go. Divided by 2,000. .00718. Oh, that makes sense. It just moved the decimal over a couple places. So now our max error is this. Now I'm not going to add it on and subtract it off again, but I want you to think about what would happen if you add it on and subtract it off. And I want you to think about this max error number, what you're seeing there. If I added .00718 to this number, what significance would these two zeros have? When you say none, you mean when you add this number to here, that won't change. And when you subtract this number from here, that won't change. Well, a little bit, right? So what does that mean? What does that mean when you have two zeros? We got 2 decimal places accuracy. Now you say, well, that'll change a little bit. You're right, this would go 0.79. But within rounding, we would have 2 decimal place accuracy. So when we calculate our max error, and our max error has several zeros in this thing, what's that telling us? That's telling us how many digits of accuracy we have. So now our max error is starting to become a little more useful. Okay? So now, again, pretend we don't know this number. We do 1,000 left rectangles. We know those first 2 are right without ever knowing what the exact answer is. And why do we know that? Because this is the worst case scenario. This is the most error there could be. Now, is it possible we have more than 2 digits of accuracy? It's possible, right? It's possible. If we're assuming, remember, we're assuming that the F graph has this slope the whole time. It's possible it only has that slope for a very short time, and the rest of the time it's pretty flat. And if it's pretty flat the rest of the time, that means the left rectangles are pretty accurate. So it's possible our 1,000 lefts might have 3 or 4 or 5 or 6. Remember, this max error is not a predictor of what the accuracy is. It's a guarantee that you have at least that many. But you might have more. Okay? Now, here's the part that gets cool when it comes to what your calculator does. The other question we can ask is how many, and this is how your calculator is programmed in, how many ends for a max error of 0.00001, let's say 4 decimal places accuracy. How many ends, how many subdivisions do we need to get a max error of 0.00001? Well, tell me what would change in our formula. So we're doing lefts again. So the idea would be, okay, how many lefts? K1, what do we put for K1? That doesn't change. That's still 3.59. 2 minus 0 squared, all over 2n, because we don't know what n is, right? Less than or equal to 0.00001. And we basically then have to solve, which we can just get on our calculators and do. Now, it's an easy one to solve. We just multiply this over, do it. But we can just type in our calculator solve as well. So let's go into our calculator and let's just type that equation in and have it solved. Yeah, we can use x, that's fine. You can do less than or equal to. I like doing less than or equal to. You could just do equal to, and we'll talk about what that means. But we go 4 zeros, comma x, we're solving for x. We hit enter. And x less than 0, of course x won't be less than 0, that's a number of subdivisions, you can't do that. And what's it say, 718,000? Greater than or equal. Now what if that would have come out and said 17.1? X has to be greater than or equal to 17.1. What would you have said? You'd have to round up to 18, right? Because you can't have 17.1 rectangles. And what it's telling you is you need 17.1 rectangles to guarantee that accuracy. Well, you can't have 17.1, so you need 18. 17 would do it. So you have to round up to 18. Right? That's why I like the greater than or equal to. If you just do it as an equal to, I could see you just leaving your answer 17.1. Well, that doesn't make any sense. You can't have 17.1 subdivisions. Right? You have to have a whole number of subdivisions. So it takes 718,000 left rectangles in this problem will guarantee us 5-digit accuracy. And that's how the calculator does it. How does the calculator know that those 13 digits it gives us are accurate it does it by doing a worst case scenario formula like what we just did right there. Okay? So it does that calculation, says, okay, we need 718,000 left rectangles to do it. Let's do a left rectangle approximation with 718,000 and spit out the answer. Now, it's not going to do left rectangles because that takes too long, right? Your calculator would be bogged down all the time, every time you did an interval. So it does something better. Midpoints and trapezoids are better. Simpsons is even better. There are some more complex ones, I think, other than Simpsons that are even better yet. Okay, and so I think it's programmed with those, but you get the idea. All right, back to your Theorem 3 notes, because there's a couple that we need to add here. What about for midpoints and trapezoids? So there's two of them, actually. So let's do midpoint and then we'll do trapezoid. So the max error for a trapezoid, and this is on page, this is on your page 387. The max error for a midpoint is K2. We'll talk about K2 here in a minute. B minus A cubed all over 24n squared. And the max error for a trapezoid is K2 times B minus A cubed all over 12n squared. And the reason the midpoint has a bigger number on the bottom is because it has less error. Think about it, if you divide by a bigger number, you get a smaller answer, and a midpoint has smaller error than trapezoid. We talked about that earlier. Midpoints are roughly half as accurate, or twice, I guess you would say, as accurate as trapezoid. Okay? Now, those are the formulas used there. Now, what's the difference? Why K2? Well, I'm not going to go through all the ways of deriving it like we did for the other one, but it would look very similar. What causes a trapezoid to be off? Concavity. And this is something we've never really talked about. How do you measure concavity? Think about it a second. If you have an f prime value of 2 versus an f prime value of 5, what's that tell you about f? Slope, right? One slope is 2, one slope is 5. What's that tell you? It tells you about steepness. Which one's steeper? 5, right? This is something you learned in Algebra 1. You got a slope of 5, that's steeper than a slope of 2, right? So f prime values have significance. But you know what? We've never talked about that with f double prime. What if you had an f double prime of 2 and an f double prime of 5? All we've said is if f double prime is positive, then f is what? No. If f double prime is positive, what's f? Concave up. But what's an f double prime of 2 mean compared to an f double prime of 5? F double prime of 5 is more concave up than an f double prime of 2. What does that mean? It's more curvy, to be technical. Right? It's more curvy. If the higher, right? If f prime has a higher value, that means it's steeper. If f double prime has a higher value, it means it's more concave. It's more curvy. Well, think about it. If this graph would have this amount of error, but another graph might come through here, whoops, and do that. It's more curvy. It's got more error. So the higher the f double prime values. So when we want to do our worst case scenario, we want K2 to be what? We want K2 to be the max of f double prime. That would be the most curvy. And that's why we call it K2, make you think of second derivative. So you would do, in solving a problem that uses midpoints and trapezoids, you do the same thing. You would graph f double prime, right? Think about what Sam did for us. He graphed f prime, zoom fit it, and saw where it was a max, or min, whatever, right? Well, we would do the same thing for a midpoint trapezoid problem, except we graph f double prime. And you can use a calculator to get the second derivative for you and all that stuff. But graph it, zoom fit it, and pick that highest number. And round it up, and that's what you would stick in the K2 spot. Okay? And it's the same idea. It's a worst case scenario, and it's a max amount of error. All right. That's all I got. So, your homework, and you've got a lot between now and next Tuesday. Somebody said something about some classes have research papers or something.
Yeah, probably.
I don't know. Are they due like next week or something? Was there somebody's English class in next week? Regular English. Somebody, yeah, anyway. Well, the point was somebody said, oh boy, that's a lot of work to do over the weekend. I got a research paper. I said, hey, here's the deal. You got another 30 minutes or more to work on this. So this is 6.2. That's really your assignment for tomorrow. And I'm going to be at a track meet tomorrow, so I won't be here to check it. But that's your assignment for tomorrow. And then tomorrow in class, you get to work on the assignment for next Tuesday, which is to do all the multiple choice in this next packet. Anybody else want their green? All right. So, this is sample 3. Who needs one still? Okay. Yeah.
And so these kids on the service trip basically got all this at once.
Now, are they going skiing?
Yeah.
Well,
I have one.
they'll give them something to do on the bus. All right. Because Mandy knows about that. She's going to have to do it on the bus. All right. Oh, you got all. All right. So anyway, tomorrow your assignment with the sub will be work time on all those multiple choice. Now, on the actual AP test, for those 45 questions, you would have 50 minutes for the 55 minutes for the first part and 50 minutes for the other part. So that's 105 minutes. So with 90 minutes of work time, that's only 15 extra minutes, right? Now it might take you more than that, but who knows how hard you work on it. But okay. All right. Now there might be a problem or two in there that we haven't learned, and there's probably another handful. Hopefully not too big a handful that you should know how to do, or you've at least been taught the various techniques necessary, but whether you can get them or not is a whole other thing. But that's why we're reviewing. But if you get the one that says, for example, the volume of a solid revolved around an axis, we haven't done it. But you will find out as you go through here, there's not very many things left that are on the AP test we have not at least talked about. Okay? Now, I would hate to take the AP test right now, if I were you. But we'll get there. Okay? But this is part of that process. All right. Rest of the time's yours to work.